All right, I'm just going to pick up where I left off last time and get through that first week's worth of slides since we're into the second week already. Right there. The last thing I want to do at the end of today's lecture is, yeah, I only got through like 12 slides last time. Right there. Is I want to go through and demonstrate how to write a program, how to compile it, and how to run it, since that's going to be the key of what you're going to be doing right there. So I already talked last time about, actually I went a little further, about the input units, the output units, the memory unit, and then of course the ALU is the microprocessor itself. So those are the four basic components of a microprocessor or a computer system. Input, output, memory, both primary and secondary, and the ALU right there. And since we don't have a final exam, I can't say that that's going to be on the final exam right there. So, okay, and the CPU is part of the ALU is actually part of the CPU right there. And it's not really that critical that we look at that there, but we have our input. My handwriting is terrible here. Matter of fact, let me just take the keyboard off for now. Put this down to where I can write. Input. I'm just going to call this the CPU. And inside the CPU is the ALU, the arithmetic that does the math, but that there. It's really one chip in any modern computer. So it's an i5 or i3 in most Intel computers. It's an ARM in your phone right there, but it's a microprocessor. That's what they call it, the CPU right there. We have our output, and pardon me, but I write like somebody who had a stroke 4 months ago. That's because that's the way I did have. We also have two types of memory. We have our RAM. RAM is your memory that you scratch pad that the CPU uses as its student. Okay, that there. And then we also have our secondary storage, and I'm just going to put that as disk right there. It may not be a disk anymore. It might be, solid state drives. That's what your phone uses. That's what this laptop uses, is a solid state drive. Or it could be a physical hard drive. Or it could be a thumb drive. It could be any of those right there. So those are our basic components to our computer system right there. Okay, now we get into something a little bit more complicated, and that's our data hierarchy. Now, data hierarchy is the way that information is stored. We're not going to do a lot with that in this semester. That's really a more advanced topic in computer programming and database management, but let me just kind of go through and talk a little bit about that. The smallest thing that we have in a computer as far as memory goes is a bit. That's a single 1 or 0. You don't do much with bits up there. Then we progress to 8-bit characters or numbers, and then we go on to fields and larger numbers, either floating point or integers. So we have all kinds of different types of data. And we're going to look at a number of those as the class goes on right there. But this is kind of a type of data hierarchy. We have a record. A record is one person's information. So if we look at a student, for example, in this particular case, we're looking at Judy Green. Judy Green's first name is Judy, and Judy is made up of 4 characters. Each of the 4 characters is made up of 8 bits right there. So as we look at computers, we go from largest, smallest to largest. The smallest is a 1, 0, 1, 0. And 8 of those make up a character. And it just so happens that capital J is binary 4, 6. 4A. 4A is the hexadecimal code in ASCII for capital J. And we'll talk later what's meant by an ASCII character, but it's an 8-bit number. In this particular case, it's 4, and my pen is doing weird things right there. 4A, and that's a hexadecimal number. And some of you might have heard what's meant by hexadecimal, but it's a number that goes from 0 to 15, and we use letters for 10, 11, 12, 13, 14, and 15, and A happens to be the number 10, which is represented by binary, and this is actually not the right pen for this computer, but 4 is equal to, oh, this is not good, 0, 1, 0, 0, and pardon my hand. Now my handwriting is not good, but now my pen is not working right. So anything I write is going to be complete garbage. That there. Somebody will say that anyway. That there. So our field is one part of a record, and a record is everything that deals with Judy. So Judy Green is first name, last name, probably then there's her IC number, then what her major is, and on and on. And all these fields combined form a file. So we can create a file of all the students in this class, for example, right there. And they're made up of different, each record represents one student, and each set of data regarding one particular part of data for that one student represents a field within that record. That's there. Now, we're not going to get into database programming. We probably won't do a lot with this, other maybe toward the end of this first half of the semester, but again, we keep in mind, and I don't know how long this session goes, because we started 2 weeks after everyone else, so I don't know if we're going to go 2 weeks longer or if we're going to get short 2 weeks, but we'll see how that goes at there. They haven't told me when this class ends. Right there. So again, this kind of goes back to bits is the smallest one, 1 or 0. Characters represent 8 bits right there. The character sets are based on ASCII right there, and the ASCII set is goes from 0 to 255, because that's what you can represent with 8 bits. It includes all the letters of the alphabet, upper and lowercase, all the numbers 0 through 9, all the special characters, and including Greek letters and some Arabic letters at there. So, all computers represent or use this type of architecture right there. Back when I first started using computers, we actually had to work in binary or ones and zeros. And then we were able to move to hexadecimal, and then we could start writing compile programs and working with strings. That there. Unicode is actually another term. So fields is that there, again, it conveys meaning. A record, again, is, like I said, everything dealing with, and it doesn't have to be a person, A tool in an inventory would have an SKU, have a part number, it would have a description, it would have a price. So our data hierarchy, it doesn't just deal with people, it can deal with things, it can deal with places, it can deal with temperatures in a certain location. That there. So that there, and of course a file is a group of related records right there. So we're not there. A database is a collection of data organized for easy access and manipulation. So I can create a database for all the students in the UniKL, for example, and inside that database I would have a record, a file that would contain all the students. Then I could have another file for this class containing the IC numbers of all the students in this course. And then I can have a list of assessments for this course and grades for each one of those assessments for each student. So I can keep going larger and larger with this database. I have done database programming. It's not my favorite thing to do, but I have designed databases, and I've maintained databases, and I've wrote databases, so I'm familiar with that. Big data is something relatively new. It's a new term, and it deals with large amounts of data. Out there, you keep hearing the term big data, and the other term is data mining, where you could dig through a lot of information, a lot of data, looking for particular things. Companies like Google specialize in big data. Facebook specializes in big data. So in Facebook, for example, they would have every Facebook users, all their messages, all their friends, and that's a huge amount of data. And then, of course, they mine that data to know where you shop. They get to know the places you've been to, where you shop, and your friends, so that they can send you advertising for the stores that you go to. They know that you like shoes, so you'll get shoe ads pop up on your Facebook page. I like to buy electronic gadgets, so I keep getting ads from Lazada and Banggood and these various advertisers, and they know to send advertising to me because I've shopped at those stores before and I've bought things from those stores. But big data is, again, beyond the scope of this course, and actually database design is beyond the scope of this course. And that's more of a desktop computing area. As I mentioned earlier, I'm an embedded person. I deal with hardware most of the time, and it comes from being an electronics engineer and not a computer programming, being a computer programmer or an IT person. So some terminology, this is just up there for your information. You'll notice that the term kilobyte, when we talk about kilometers, that means 1,000 meters, right? In the data world, it's 1,024. So the term kilobyte is not exactly 1,000, but it's 1,024. A megabyte is 1,024 kilobytes. And you'll notice that this actually, it actually goes with 2 to the 10th, for example, right there. Because we deal with ones and zeros is a binary number. It has two values, 1 and 0. So the number of digits that we deal with, there are 8 bits, actually goes from 0 to 255, right there. So 10 bits goes from 0 to 256. I mean, that 256 goes from 0 to 511. That there. 9 goes from 0 to 1023. It doubles every time we add a bit. That's why these numbers are like this, right there. And it kind of confuses people because you buy a 4 terabyte drive, and Windows uses this notation, but 4 terabytes is actually going to be less than 4 billion right there. It's going to be, on Windows, because they're using terabytes as 1,000, right there. Right there. And this is using 1020. So it's just, the numbers are a little that there. It doesn't really affect life as we know it. We don't really worry too much about that. It's just that there is sometimes a difference out there, and you'll see it when you buy a piece of hardware and it says it's a 4 terabyte drive. You format it, and it doesn't say 4 terabytes. It says 3 terabytes and so many bytes right there. So you think you got short change, but that's because the person selling the hard drive uses that 10, time, 10 to some power, 10 to the 12, where the other one is using 2 raised to another number right there. So those numbers are just off a little bit. We don't need to worry about that for this class, but just keep in mind that sometimes our numbers won't match what you get in your engineering courses right there. They're going to be a little bit different. Okay, now we get into our programming. We have 3 levels of programming languages. Machine language is our ones and zeros or hexadecimal. I've written in machine language. Back when I wrote some of my first programs for the 8085 back in the 80s, we would actually sit down at a hexadecimal keypad and put in 3A, enter, 2C, enter, 4C, enter. Then we put 1000, go, and tell it to run the program starting at address 1000. And we wrote our code in machine language. Back a generation before mine, we would actually toggle switch and then push the enter button. Toggle switch. And I've seen some of those computers. We actually had one at our university I played with, with Altar, one of the very first home, I wouldn't say personal computers because it was about this big, but it was based on the 8080, and you had to program the thing in binary right there. I don't miss those days, and we don't want to worry about those days right there. The one thing about machine language is that each microprocessor has its own language. So anything written in machine language is not executable on a different microprocessor. So if you wrote something for an x86 system, which the i5, i7 series, the newest generation, are outgrowths of the old 8080, 8085, x86 architectures, those x86 type programs would probably run on those, except for Windows would have a problem. Windows 10 would not run anything at that level. But each computer understood only its own language. And that was because the microprocessor was designed that way. So a Z80, which was I wouldn't use the Z80, but the 6800, which was an old Motorola processor, would not run 8085 code. It would not talk, you had to rewrite the code from scratch. Not very efficient, right there. So machine languages go down. Now, ultimately, all programs are compiled into machine language still today, with the exception of Java and Python and a couple of the interpreted languages. We'll talk about the difference between compiled languages and interpreted languages. So now, programming in machine language was tedious, slow, and prone to errors, right there. So they developed a language that was a little bit friendlier, it's called an assembly language. Now, assembly languages are languages that are, again, still unique to a particular microprocessor. Back when I first started programming, we would actually write our code in assembly language. And assembly language instructions would include things like move the contents of B into A. And A and B are registers in the microprocessor. So we would have instruction that would look like, and I know I shouldn't write this, but I'm going to write it, move A, comma, B, right there. And so you can't read what I wrote, but as I wrote it, you at least heard, I said that this is move, and this is move into A, whatever's in B. It actually goes backwards So I would write my code that way, and then I would hand assemble it into hexadecimal numbers, and I would enter it into the microprocessor right there. So assemblers translated machine language or assembly code into machine language. That was called an assembler. The assemblers that I used when I first started programming was a little card that listed all the instructions for a microprocessor and what its hex codes were. So then I would hand assemble it. And then, of course, later on, we got assemblers that would read a text file with our assembly language code, and it would then output the machine language. Again, not very friendly, and again, unique to each microprocessor family right there. So you couldn't move from one processor to another. You'd have to start writing the code from scratch right there. It's clear right there. Then high-level programs came out. Now, high-level programming was a series of languages such as C, what we're going to be using. C's been around a long time. One of the most common languages, high-level languages that was really popular back in the early days was Fortran. And those were written in a language that followed a much more English-like instructions. And I'm sorry, but I know that there are no high-level programming languages based on Malay. They don't exist. The market isn't large enough for anybody to develop a high-level language based on Malay. Actually, there isn't one based on Chinese either. Almost all the compilers are based on English, right there, programming languages. So I'm going to teach people whose native language is Malay in English, a language based on English but isn't quite English. So it is a little bit different, and I can see why people, why some people don't like programming, but it's not that difficult. We'll get through it quickly. So compilers convert the high-level language into machine language. Ultimately, it has to be machine language, otherwise the computer can't understand it. So we go through a process where we run it through a compiler, and then we'll talk about a linker, and then we end up with machine language that runs on our computer right there. But we go through that process. Now, there's a number of languages out there. They're called scripting languages or interpreted languages. Or they run through an interpreter, which means that on your computer, there's a program that reads the code and executes it line by line as it's running. Now, interpreted languages run much slower in real time because it has to interpret. If I'm talking to my son in San Diego in English, he doesn't have to translate it. He doesn't have to think about it. We're talking the same language. I talk to you, some of you are sitting there going, what am I saying? Because you're translating in your mind English to Malay as I speak. You don't think in English. It's the same process that there. As we go through a scripting language, every command has to be interpreted as the command's being executed. When we compile it, we translate it into the native language of the processor, so it runs it very fast. So compiled programs run much quicker. They also require less memory on the drive and everything else than interpreted languays. Scripting languages are very popular for web-based programming. The reason is that if I'm going to write a program that's going to run in HTML or through a web page, then I don't know what type of computer, or even if it's a computer or a phone, the person's going to execute this code in. So you have a Java runtime library that interprets Java instructions and executes them as they're running. So Java is a much slower language than C. Java is not necessarily appropriate for embedded systems because I would have to put a Java interpreter in every system and include my programs in Java text-based text files. So most people still write in compiled languages that don't execute, that aren't interpreted at runtime, but they're compiled into runtime programs. Anytime you see a .exe at the end of a program name, that is a binary file that's got the machine code to run the program. If you see a .j, for example, or is it just .j? I don't work in Java that much, but if you see a .js, I think it's .js for JavaScript, that's a text file that contains Java instructions right there. So we're going to be working with a high-level language. And actually, I call C a high-level / low-level because we can write some very low-level instructions in it. Right there. C programming was developed for 2 previous languages. It's been around since about 1971, 72. It was developed by Bell Laboratories. Bell Laboratories was the phone company back in the U.S. That there. It's named after Alexander Graham Bell. That there. And one of the earliest uses of large computers were telephone switches. That there. You know, if you dial a number, the computer would then route the call to where it was supposed to go. And Bell Labs, that there. Bell Labs was at one time the largest privately funded research organization in the world. Bell Laboratories is known for not just C programming languages and Unix. And Unix is still around today because anybody that uses a cell phone uses a form of Unix on it. You know, Android is a form of Linux, which is derived from Unix. Mac OS is also a form of Unix. So almost all cell phones are based on a Unix-based architecture, so they've been around. And Bell Laboratories developed that. So, you know, it's not, there are desktop computers that run Linux as their primary operating system. That's there. I've run Linux as a desktop computer. It's a very nice operating system. It's not as widely supported as Windows or Mac OS. And you can't get things like Office for it. They have something called Open Office for it, or I can't remember what they renamed Open Office to, but it's there's an Office look-alike that runs on Linux that isn't quite as robust as full-blown Office. There's a version of Linux that runs on the Raspberry Pi, which is a very small microcomputer that's the size of a credit card. And again, that there. So with that, there. But C was developed. Kearney and Ritchie came up with the first version of that right there. That there did Dennis Ritchie, and actually he had a partner there that they mentioned. He says 82. It was a programming language developed for Unix, to develop Unix operating system. Many operating systems are still based on C or C++. Now, C++ is an extension of C, and we'll talk a little bit about C++. C++ is more abstract than C, right there. So I won't, and there's some major differences between the compiler we're using and Visual Studio's C++ compiler. So when I tried using C++ in this class, it was a disaster. So I went back to C. It's mostly hardware independent. Now, when I say mostly, every program that we write in C in this class will run on a Mac. It will run on any other microcontroller. However, if you're dealing in the embedded world, you sometimes have libraries or you write functions that talk directly to hardware, and that, again, varies from processor to processor. That's it. So with careful design, it's possible to write C programs that are portable to most computers. So it's not 100% hardware independent, but it's a lot better than machine code. If I write a C program for a Windows machine and I want to port that same program over to a Linux machine, it's not that big of a deal. If I want to port that program over to run on an ARM microprocessor instead of a i5, i7, it's not that big of a deal. But if I had machine code, I'd start from the beginning again. If I have assembly code, I'd start from the beginning again. So C is usually used because it allows us to do things that some of the other languages don't. There's a lot of languages out today. A lot of languages out today. Java's out there. Python's out there. I taught a little bit of Python last semester in my microcontroller course, for example. There's Java's out there. Of course, Java's an interpreted language. BASIC is still around. BASIC was one of the early computers. And probably there's more code written in BASIC than there is any other language today. BASIC is still a very popular language right there. C is built for the performance. It's one of the languages that it was really designed to run fast and to be memory efficient and to be very, very small and compact. That's why it's very popular in my world, in the embedded systems world. Up there. And it also allows us access to the hardware if we need to. There's languages out there like Pascal is an old language, Java's another one. They don't give you any access to the ports. You can't write to the keyboard directly, you can't write to the mouse, you got to go through the various libraries. C allows me to talk to the microprocessor directly if I want to. So C has got some low-level architectures that allows us to do that. So real-time systems are almost always written in C. And as I said, my world works almost exclusively with C or C++ to a degree, right there. Digital signal processing, where you have to do a lot of fast number crunching. C is, again, the primary language because you need something that's very, very fast, right there. A lot of the other languages, as I said a minute ago, BASIC, in particular Visual Basic, is used a lot today because it's quick and dirty and easy. But Visual Basic is much, much slower than anything written in C. Much, much slower. Takes up a lot more memory. So C is the choice of languages for electrical engineers that go into any kind of embedded system. We almost exclusively work with C or some version of C, right there. Okay, some more terminology right there. The operating system is that their C's portability makes desirable input that they're Linux, Windows, Android, Apple. Those are all operating systems. The operating system is a layer of software that resides between your program and the hardware. So the operating system has to talk directly to the hardware. So if I want to draw a circle on a screen, it's got to talk to the hardware, and there's a command where I can tell it to draw, through a graphics library, I can tell it to draw a circle of a certain size on the screen. That's there. I don't have to go through and talk to the graphics card and turn on and turn off each pixel on the, on the graphics controller. That's all done within the operating system. That's there. Different operating systems, of course, require programs that are developed for that. You can't run a program developed for Windows without recompiling it for Android to run on an Android phone. You can't run a program developed for Android on a Windows phone or a Apple phone, an iPhone, right there. Those all are different operating systems, and the programs have to be compiled. Even though the C at the top level may be the same or almost the same between the Android program and the iPhone program, they have to be compiled with different compilers and targeted to that particular operating system. Now, an operating system will also allow us to run programs compiled for that operating system on different platforms that run the same operating system, even though the hardware is different between each one. each one there. I could run a Windows program developed for these computers that probably run an old i5 processor, have a separate graphics card on this little tablet. It's also Windows based. The hardware is completely different right there. The graphics card is completely different. But the operating system takes care of those differences. Now, in the embedded world, we may not necessarily have an operating system, in which case we have to talk directly to the hardware. The right there, let me just kind of circle this right here. I didn't get the next line there. The vast majority of microprocessors produced each year are embedded in systems other than general purpose. So as I said, my world is the embedded systems world. The embedded systems world is actually much, much larger than the computer world. If you look at the number of microprocessors that are contained in the ignition control system of your automobile versus the number of desktop computers or even cell phones, there's a lot more in cars. If I look at all the microprocessors that are out there in microwave ovens, in television remotes, in DVD players, washing machines, refrigerators, the embedded world is actually a much larger universe than the desktop computer world. Now, this is kind of blended a little bit as we get into, cell phones, because cell phones started off as an embedded system and they migrated it into a full-blown operating system and computer system. You can't argue that an Android cell phone is not a full-blown computer system. It does everything that a computer system did 25 years ago. I mean, I can hook up a keyboard and an HDMI monitor to my cell phone, and I've got a 3-4-year-old cell phone and use it like a computer right there. But again, this gives some examples. Navigation systems, smart home appliances, home security systems. Now, he put smartphones in the embedded world. I've kind of moved the smartphone out of the embedded world into the computer world. That's my personal opinion, is that unless you've got an old dumb phone, that they're a fairly older phone, it's actually a full-blown computer system. And I don't know of too many people your age that don't use some type of high-level smartphone. You're either using Android or iPhone, one of the two. Those are the dominant players, and I consider those computers. And they're actually computers that one of their programs happens to make phone calls, right there. And I could venture to say that 90% of the people probably use the cell phone feature of their cell phone, or I call it cell phone, that's what we call them in the U.S., hand phone, that they're probably 90% of you probably use all the other functions more than you do the actual phone itself, right there. Texting is a computer is a computer operation, right there. Emailing is a computer operation. Taking pictures is a computer/camera operation. That there. Playing music, MP3 function, that's used on the computer side. So if you look at the number of hours you spend using your hand phone for things other than making phone calls, I would venture to say, as I see, he's got his out, she's got hers out. People are using their hand phones even during lectures. That the phone part, which was the primary purpose of a hand phone when it came out 20 years ago, is probably a minor feature of most hand phones. When I read hand phone reviews, smartphone reviews in magazines, almost none of them talk about how the quality of the phone service is. I mean, if you think about, read the latest reviews of, say, the Samsung Note 8, which is supposed to be released. They're saying maybe later this week even. The Note 8 is supposed to be out, or September 15th. I'm reading different release dates. But the Note 8, all the reviews of the Note 8 or the Samsung 8 phone, or the latest iPhone, the iPhone 8 sent out, so it hasn't been reviewed yet. But all the reviews, they talk about how fast the processor is, how much memory it has, the quality of the pictures. They talk about the type of speakers that are on there, the playback. They talk about the web browser and how responsive it is. They talk about the screen and how nice it looks, how well it does at playing videos. Almost nowhere in any of these articles they mention the quality of the phone itself. That's there. So that's why I don't consider smartphones, phones as much anymore as I do computers that make phone calls. Out there. And and I read a lot of reviews. I'm a tech person, although I still use a Note 4. That's what 3 generations back or so. That there. There's a reason I haven't upgraded my phone, because I carry a lot of music, so I like the expandable SD card. And the Note 5 didn't come up with the expandable Note SD card. Note 6 they didn't release. And the Note 7 tended to blow up, right? So I'll be looking at the Note 8 to decide whether I want to buy it or not. But again, he gives anti-lock brakes, the airbags. So the embedded world is a huge world for that there, and it's not as big a world for electrical engineers as electronic engineers. Now I come from the electronics world out there, and I'm an embedded person. But also in the U.S. and UK, you don't have too many electrical engineering programs. You're all electrical and electronic engineers, or they just call it electrical engineers, and it's mostly electronics out there. So, a real-time system. These are systems that have to do things very quickly. They're called mission critical. That comes from the aerospace/defense world, mission critical. These need to work continuously. They need to go in real time, and they have to operate correctly and very quickly. They can't have glitches and delays. So if you look at the guidance system of a 787 Boeing aircraft, right there, you can't have a delay from when the computer says a flap has to go up from the time the flap goes up. Otherwise, the plane could crash. So these are all mission critical. I would have to say in that category, something like an anti-lock brake system would be mission critical, right there. Because when you push on the brake and that brake, and let me explain what anti-lock brakes do. It probably doesn't mean as much to Malaysians as it does for people from Minnesota. I grew up in Minnesota, which is the ice and snow state in the U.S. I mean, it gets very cold, and we quite often would hit our brakes on ice and snow, and if the brakes locked up, then you would lose control of the vehicle. So anti-lock brake systems monitoring the wheels, and they bring the car to a stop quickly without locking up and causing the car to skid and do a 360 and ram into a tree. And trust me, I've been in cars where I've hit the brakes and they've locked up and I've gone into skids. Fortunately, I've never hit anything in a skid, but I have done a couple 360s in the middle of the road and never hit anything. But anti-lock brakes have to monitor the wheels in real time and have to release the brakes. They pulsate the brakes to keep the brakes from locking up. And when you drive on ice and snow, that's a huge issue. As far as I know, I haven't ran across any ice and snow since I've moved to Malaysia 3 years ago. It's not a common thing. But in Minnesota, in January, I guarantee there's ice and snow abound. Communication systems, again, your cell phone is an example. Your speech is digitized into digital signals and transmitted over the airways. It's received at the other phone. It's converted back to analog signals. That's there. A webcam is another example. A camera is that there. But again, these things have to be run smoothly, quickly, and that's where languages like C come into play. All right, that's it. Because C is hardware independent, blah, 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 blah. C can also run in a wide range of computer. That's just a comment. Okay. We're going to be getting into starting to talk C in particular here. And I don't know if I'll get through this whole, I've talked for 44 minutes already. I can't believe how fast this goes. And I talk fast, don't I? Most of you think that I talk fast, right? All right, C is made up of little pieces called functions. That's there. We're going to learn how to write functions later on. Chapter 5 talked there. Inside the C standard library, there's a whole bunch of functions. There's a function for reading the keyboard called scanf. There's one for printing to the console called printf. There's all kinds of that there. There's a function called sign that calculates the sign of a number. There's a function called square root for calculating the square root of a number. There's a whole bunch of functions in the C standard library. And we have to include the standard library whenever we write a C program. So we're going to be looking at the building block approach or modular program design, is that we don't write large programs all in one place. We write a large program out of pieces of little programs right there. So that's there. We avoid reinventing the wheel. We use software reuse. Software reuse means that if I write a function that is usable, I stick it in a library and I can reuse it. The best company that I ever worked for was General Electric. And General Electric is a large company. I'm sure everyone's heard of them. But when I worked for them, and I was working there as a consultant for about a year, off and on, not full-time, about 3 months full-time in summer, and then about another 10 months part-time, that they're on a couple of projects. They require that every function that I wrote was formatted in a particular way, not quite as picky as CQI is here on this campus, that there, but they had a certain format you were supposed to follow in terms of documentation. And every function that I wrote went into a software library that the company maintained, and every other designer in the company or engineer in the company had access to this library, can search on keywords that I was required to include in that there on what the function did. They can read my header for the function and tell whether or not that function was usable for their particular program, and they could steal that function and reuse it. They could steal the function and rewrite part of it if it wasn't quite perfect. And that's called software reuse. And a lot of what you want to do is try to reuse as much as you can. Now, as students, you're discouraged from doing that to a large point, because if I'm writing a term paper or a research paper, I can't steal your research paper from last year and just reword part of it. I'm supposed to rewrite everything from scratch. In the software world, you don't want to rewrite every function from the beginning. You want to try to reuse as much as possible. So we have the standard library functions. Those are supplied to us by the compiler people right there. They're part of the standard library. There's functions that we write ourselves, which again, those are unique to our program. And then again, there are functions that other people write and there are companies that actually make a living selling nothing but libraries. They're a series of functions. They're not as prevalent today as they were a number of years back, but for example, if I was wanting to do image processing and I didn't want to write a lot of the functions to do discrete cosine functions or data compression, I would buy functions, a image processing library from various people. Now, in MATLAB, that still exists, and they call them toolboxes. MATLAB toolboxes are actually nothing but libraries of various functions that that MATLAB sells separately from MATLAB. If you buy a MATLAB, you'll pay 10,000 ringgits, and if you want the image processing library, you'll pay another 5,000 ringgits. If you want the speech processing library, you might pay 2,000 ringgits. If you want the robotics library, you pay another 5,000 ringgits. But they charge for each library right there. And that's why when we get into MATLAB, we won't be using libraries much because we don't have a lot to pick from. Matter of fact, we probably won't even use MATLAB. We'll probably use Octave instead. So that's down the road. All right. Creating that there, disadvantages is kind of time consuming. I won't read that there. And I know I won't get through all these slides. I'm only 36 through 119. That there. You know, again, it takes time to go through these slides. That there. But it's important that I do go through them. That there, because our base is important. That there. So again, we're going to be using standard. That there. Some other languages. C++ was developed at Bell. That there, it provides what they call object-oriented programming. That there in classes, it's much more geared toward reusability. It has a lot of nice bells and whistles. Some of its features been around. The syntax is different than standard C. Now, and so we have to be sure that when we tell our C compiler that we want to, write a program that we're going to write in C instead of C++. And I don't think I'll get to it today. But I was going to try to show what I might give a quick little demo later at the end. But C++ is a more modern language, right there. Most people in the embedded world are still using C, but C++ is kind of picking up steam right there. People that are developing operating systems tend to use C++. Right there. People that are doing database design, and I'm sorry, but the right side of my face is getting a little bit numb, which happens to be once in a while out there. That's part of the residuals from having brain damage out there. And I joke about that, but that's, stroke is essentially brain damage, so I get some numbness there. So that's why I keep itching my nose up there. So the last half of this book covers C++. We won't get into that. So object-oriented C is kind of an early version of C++. It doesn't really exist anymore right there. It's used in the iOS but they actually don't call it that. It's something else. And I haven't done a lot of iOS programming. Java, I mentioned earlier, that's based in C++, but it's an interpreted language, and it's very C-like. So anybody that is familiar with C can easily migrate to C++ and can easily migrate to Java. C# is unique to Microsoft. C# was a language developed by Microsoft for web programming, and it was designed to replace Visual Basic. It really hasn't taken off that much. And we won't talk. They do mention that there are some non-Microsoft versions of C#. I've never seen them. I've never used them. And I've used C# just enough to see what it's like, but I've never really done anything with it. My yardstick on learning programming languages is the jobs that I've done where I'm paid real money to do programming. Then I learn the language very well when someone's giving me, money in hand for doing a project. Then I learn the language really well because I'm getting paid to do it. Then I'm doing a real product that's going to end up out in the market or being used in a company's factory or whatever. So those are the products, languages that I've become most familiar with. And that's also a good indication of which ones are being used, because those are the ones that people are willing to pay people to design systems So that's why C has been the primary one, along with some C++ projects right there. So Java, I've never done much with web programming. Java's really more on the web programming side right there. PHP is almost exclusively for web developers. Python I started using a little bit last year, And Python is a scripting language, but it's used a lot on the Raspberry Pi, which has become a very popular platform for hobbyists and students and that there. And I want to move the microcontroller course to the Raspberry Pi instead of the old 8051 or X80 system, simply because that there. So I've been using Python. Again, Python is very C-like, but there's some unique differences that make it a little easier. It's an interpreted language, so I would probably never use it in an embedded system unless it was an embedded system that uses the Raspberry Pi. JavaScript is probably the most popular scripting language. It's by the term JavaScript, it's Java, but it's that term. So it's used a lot on web pages. Now, there's a lot of people talking about wanting to do away with JavaScript, but Sun Microsystems maintains the JavaScript libraries, and Sun is a big company still that in the Java world. Other languages, Swift, and I mentioned before, Apple doesn't use Object-C anymore. Swift is what Apple now uses for iOS programming. And I have never used Swift right there. It's only been around for 3 years. But if you want to write iOS programs, you have to learn Swift right there. And that makes life interesting because Android still uses either Java or C as its primary platform, and iOS uses Swift. So porting software programs from Android to iOS and back and forth is not as easy as if they would have shared the same platform. They don't. Apple, and you can't get Swift, as far as I know it, on anything but a Mac. So if you're going to write Swift software and sign iOS, you have to buy a Mac computer. And I have a small Mac Mini just for if I ever ended up in a situation where I had to do my iOS programming, I can use my Mac Mini. I'm too cheap to buy a real Mac. And I had a real Mac at my last job. That's what I had as my desktop computer. So I had a 27-inch iMac, and I absolutely loved that computer. But I ran Windows on it. I actually ran a program called Parallels where I could go back and forth between Windows and Mac OS, but I found that 90% of the time I was in the Windows world, so I opted not to. When I left that job and they took my Mac away from me, I tried to buy it from the university, actually. I wanted to keep that computer. They wouldn't let me have it, but they gave me enough money to buy a Surface Heat laptop, so I prefer the Surface now. It's hard to carry the 27-inch iMac to the classroom and use it for lecture. So objects, I'm going to skip this discussion on objects for the most part, but an object is an object, is a thing, or it's a software component. I guess I'll use this term, or reusable. An object might be something like a car or a person, and they have different attributes to them. And a car, and we have classes and that terminology is really beyond the scope I want to go into right now. So the automobile is an object, and you can design a process for that object, such as accelerate, and accelerate means you push the pedal, and that there. So typically objects have to be designed, and all their attributes and all the processes go to. Once you have an object, then you can have different features for that particular object. That's more of a feature of C++ than C. C doesn't really use objects and classes right there. And you can hide parts of it there again, I'm going to skip all that there. And then, of course, methods, you want to do something, again, that's part of what's in an object right there. Again, I'm going to skip that. Toward the end of the semester, we might touch upon this, but I'm not going to cover that now. This here, I'm going to skip all of this right there. So encapsulate all this object stuff, skip that. I put these notes on the slide, but just I'm going to skip that for now and that there because it has no bearing on C. It's more of a C++ object. All right, typical C development, and we'll go through all 6 of these stages, but not necessarily. We're primarily going to go through the edit stage and the execute stage, and along with that, some debugging processes. The pre-process compile, link, and load is done in the background, and we don't see it. We can do it, but there's one word in that there. We can just build our program, and that creates everything that there's. So all this right here is a single step right here in our process. Right there. So although the book program is written independently of the details, in this particular case, he's concentrating on a typical Linux-based system. There. So again, programs at there, we're actually kind of nearing. Phase 1 is we're going to use an editor. And again, the editor we're going to use is actually built into the C compiler interpreter. I call it IDE, Integrated Development Environment. It's called an IDE right there. And if you're on a Linux system or an old Unix system, VI and Emacs were the old style where you would run an editor separately. We don't do that anymore. Microsoft Visual Studio is probably the most common IDE out there, Integrated Program Development Environment, or IDE is what's up there. We're going to be using a different one. We type our program into the editor that there, and then we store it, and then we compile it right there, and then we may compile it, and that compute some intermediate code called the object file right there. So the preprocessor actually is something that happens, and what that does is check for syntax errors right there. And it also goes out and grabs any includes we have and any replacements of text. So if we do any equates, the preprocessor actually goes through and edits the file a little bit before the compiler is called. But it also does some error checking right there. So, and then once we go through that, it translates the program into machine code right there. And you can end up with compile time errors or syntax errors. Those happen as soon as you tell it to compile the code, and it tells you there's an error in your program. You forgot a freaking comma, or you put a semicolon in the wrong place. Those are the ones that drive people crazy, but those aren't the most dangerous types of errors, right? Because if you have syntax errors, your program just will not run. It won't compile. So this kind of goes through the steps. The linker is a very interesting part of the process. It's not important for this semester because we're not going to be linking multiple files together. I've worked on some large jobs where if I put all my code in one large file, it would probably be 1,000 pages long or longer right there. So I broke it up into all the functions that talk to the alcohol. This is for a breathalyzer project right there. All the functions that talk to the breathalyzer would be in one file. All the functions that talk to the hand unit was in another file. All the functions that talk to the database for syncing the database went to another file. So I had probably 10 different files, each probably 1,000 lines long or so. I don't know how, or not 1,000 lines. Yeah, that's it. Yeah, it was a big program. I mean, it was this tall when we were done with it. I mean, it was several thousand, a couple thousand pages. So each file itself wasn't that large and contained a separate, functions that were unique to that particular that there. And we would compile them separately. And the reason we did that was because it took too long to compile the entire program from scratch. You compile each file separately, and then you link them together with a linker at the end, right there. So if you have purchased libraries, you will quite often, the library, they won't give you the source code for the library because that's what they're selling. They give you the object files for it, and you would link those files to your code. So the linker is usually the last step right there. Then the loader actually loads it into the computer and executes it right there. And I typically don't talk more than an hour or so. I've been talking about an hour and 5. I'm probably going to wrap up here in a few minutes. I'm not going to get as far as I wanted to, but that's all right. The linking phase, let me finish this discussion here, right there. At their linking just simply goes through and grabs the holes from up there. So GCC is the command. I'm actually going to bail out of this right here, this guard. And I'm going to actually take a couple minutes, even though, right there, and just kind of show you. And I'll be honest, this computer has just been completely reformatted and redone. So hopefully my compiler works. I didn't get there. The compiler that we're using for this class, if I can find it. And where is it? Okay, it's called Dev C++ right there. And this is a free software package. You can download it. I'll put the link up on the Facebook page that there and the course website. If I don't remember, remind me on, we meet again, Wednesday, right? Right there. So we meet, 12:15 Wednesday, is that right? Yeah. There. But on Wednesday, if I haven't put the link up there, so you bring it up and it looks like this right here. And we'll go through this again right here. And we're going to create a new project right there. And this is going to be a console application. Everything we're going to do is going to be a console application. And we're going to make this C and make that the default language. And I'll just call it Project 1 right there. So we hit OK. And Project 1. And we'll just leave it in documents for now. I'll probably just delete it because, as I said, I got a solid state drive. I want to keep it empty as much as possible. And we're going to save right there. So what comes up here is our editor. And our editor right there has 2 lines at the beginning, and it says include standardIO.h and include standardlibrary.h right there. StandardIO.h contains all the functions for writing to the screen and reading the console and all that type of stuff. And then the standard library. If I want to include math functions, I would include math.h. So these are all the various standard library functions right there. We have one function here called main. Main is a function. That's a reserved word. And whenever we write code, we run the code, main is the first thing that we're going to. That's there. So I'm just going to type a line of code in here. And right here. And I'm just going to say printf. This is my first program. Right there. So this is a piece of code right there. And sometimes we have to play around with which one of these works with which these computers that there. But I'm going to tell it that I want to do a 64 debug. Hopefully that works right there. Right there. And then under project, right here, I can tell it to compile. And I'm just going to call it project 1.c right there. And that saves it. And expected, and it gave me an error. See, there's an error there. I forgot, and we'll talk about this later, that every executable line has to end with a semicolon. So that was syntax error number 1. So let's go back here to our execute and compile it again. Right there. And that compiled. So now it made a program that if I go to my documents, right there, you'll see that I got a program here called project 1, and it's a .exe file right there. So it created that particular program. It also created my object file, which I don't need right there. And of course, it's got my source code. So this is everything, and this is the project file. These are the 4 files, and as I said, I'm going to delete these when I'm done. Right there. So, that there. Now, inside here, I can tell this to execute. Right there. And you can see that it says, this is my first program. Right there. Hopefully, you can read that from back there. So, it executed my code right there. Right there. And that's the whole process that you go through in entering and executing your program. Right there. So that there. If I go back here to my and I execute this one here, you'll notice that it ran, but it didn't. That there. So now if you turn right around and hit this as release, as I recall. And project execute compile. It compiles, but if I execute it, it does the same thing out there. So now notice that it took 0.03619 seconds to run the program. It's fairly quick right there. So, but that's the process that we go through on how we're going to write our code. Even though the slides haven't got to that point, I just wanted to kind of show you that early so that you can see where we're going to go. What I'm hoping for is after the next session, I'm going to try to finish these slides and then let you write a program and do the same thing and let you out there. I should also, I don't know if, I've got internet in this room. If you do a search on dev C right there, and hopefully this is well, maybe I have internet access, maybe I don't. Let me reconnect and reconnect. You'll see right here at sourceforge.net and you can just download it directly from that there and install it. It's a standard out there. It's already installed on all these computers, but if you want it for your laptop or whatever computer, it's free, it's shareware, it's public domain. Feel free. all of our labs will use this particular program. The book, actually this version of the book is using the Linux C, so it's a little different than what we're doing. Earlier versions of the book use the Visual Studio that there. So some of our examples, the code is all compatible, but the user interfaces, and again, you have the option here of just executing. You can just tell it to compile and run, and it's all one step. So if I change this, that there. And I'll explain all this later. Right there. Up there. And why didn't it print the I? That's weird. File. Compile cleanly. And why did it not? All right, that's kind of bizarre. It's ignoring print int I for I. It should need a bracket on this, but let's put a bracket on there just in case. Maybe it's because I forgot to save it. There it is. It still is ignoring this. That is bizarre. What is going on right there? It should not be. It should print the number 0 through 9 there, and it's not. All right, I've got some troubleshooting to do on that there, because obviously this compiler is not working the way that I'm expecting it to work. Right there. It is the most. Okay. If it doesn't work right this time, then I'm going to. Yeah, but it's not working right. As I said, I just reinstalled this compiler last night, and I don't know why it's not wanting to be nice to me today, but it's sure not letting me run the code the way it's supposed to right there. And print that, it's not giving me any warnings, it's just not executing this block of code right there. It's just ignoring that block of code right there, and that is not something I'm used to seeing right there, but it's not the first time this compiler has made me angry. Right there. All right, with that said, oh, I talked to